And this is the main design thing, right? So kind of these goals lend themselves to the solution. So this is why we came up with a hierarchical recursive tree of subnets where you can basically get vertical and horizontal scalability. And we opted for, and you will see the motivation why we did so, two proof-of-stake sidechains. Raul was explaining that basically how you spawn a subnet is you have, let's say, starting from rootnet from L1, participants staking tokens, and basically this becomes now a proof-of-stake protocol, but not in a new token, right? So it reasons about Filecoin, Ether, and so on. And basically you are leveraging the economic or just in proof of work, for example, if you go to Bitcoin someday, energy guarantees that already extend, and basically you're making proof of stake from there. Because launching new L1s that are secure is going to be more and more progressively difficult, and we are not doing this here. Further, like beyond this, like unbounded, not infinite, but unbounded scalability, I would say, we had a requirement for this built-in subnet interoperability, so that as thousands or dozens and then even more subnets emerge, that you don't need to reason about specific bridging across individual subnets. But basically you leverage the tree hierarchy to get bridging and cross-net messaging inherently from the design. So that was also a requirement. And essentially, we wanted a simple and extensible design that made us start. So at first we built actually IPC on WASM FVM smart contracts, but then we moved to FEVM Solidity smart contracts, and essentially as the technology looks today, you can deploy it to any EVM compatible blockchain, but how the whole structure looks like makes it amenable to other chains as well. Okay, so a bit more concretely, there is this top-down and bottom-up messaging that links subnets together. And you can think of these bottom-up messages as writes. So these are checkpoints where the state of a proof-of-stake sidechain that the subnet represents is periodically checkpointed to the parent net. Once you do so, then possible security violations in a subnet are limited by the checkpoint that went to the parent. So for example, if you have a totally rogue subnet with all validators being Byzantine, they cannot roll back past the checkpoint that's made in a higher security context. And it's bidirectional in a sense that subnets are not their own ground truth. So ground truth comes from top down. So if we are scaling Filecoin, whatever happens on Filecoin mainnet needs to be propagated top down. So this is where we have actually top down reads of the state that propagates from the parent nets to child nets. And for example, if you had a reconfiguration on an L1 blockchain, in principle, what needs to happen on a subnet is that subnet needs to react to this reorganization. So currently in Filecoin, we are working on fast finality so that we don't have reorgs. But for example, this is one, if you make such a design, this is basically one of the important design points that you need to pay attention to. So it's not that trivial, by the way. And as Raul and Part and Juan were explaining, we do have these different subnets that have different, in future, different latency requirements, different. Basically, here we have a Saturn and content dissemination network with its own requirements, and on the right side, gaming subnet with its own ones. Just briefly, system architecture, Raul talked about this. We opted for a very lightweight design in which this whole communication among subnets is driven by two smart contracts. So there is IPC gateway actor and IPC subnet actor. For a particular rootnet, you have like an IPC gateway, which acts as like a centralized metadata service for all subnets that basically spawn off this particular parent net. And then per each subnet that spawns from a given parent net, we have subnet actors. And then the interaction between them is orchestrated by each participant using the IPC CLI. And you can try this out in the basically workshops today. So about trust domain, this is important, so I just want to highlight it a bit. So in principle, in order to be total independent participant in IPC, you would need to run at least full nodes across all, at the moment, at least full nodes across subnets. And if you don't want to do that, of course, you can RPC to a particular full node. For example, if you're like spawning L2, if you're an L2 user, you need basically to RPC into some full node in the L1, which is in your trust domain. So you can run it yourself. And you can imagine that, you know, if, for example, like in an ecosystem where it's easy to run full nodes like Bitcoin. So an IPC-enabled participant will run the Bitcoin full node, synchronize from there, get the ground truth from there, and basically propagate the information down. And of course, in practice, like you would have more trust. So basically in your trust domain, there would be validators that run, participants that run validators, so full nodes to which you can RPC and so on. Crossnet messages I briefly mentioned, so just to, they enable us like higher security and messaging across subnets. And this is based on this syncing with parent chains, so top down, as I explained, and bottom up checkpoints. So these are like, basically you get key protocol characteristics. So this is what you get from IPC, and then you can build your extensions later on, like custom consensus and so on. So what you get is a recursive tree of proof of stake sidechains, and the staking in principle is done from the L1 token. So you could do, in future, we could do staking in, for example, ERC20 token that's not a native token in L1 and down, but in principle, we wanted to have higher security guarantees by actually leveraging existing tokens. Data availability in many scaling solutions, as we will see. So I'm just giving you a brief overview of IPCs, and then we jump into comparison with others, right? So as you will see, for many of them, data availability is a challenge. We are solving it here by keeping the data, like input data that is actually inherent to a subnet, replicated across validators and full nodes of a subnet itself. So it's like data availability is taken care by the subnet itself. And security, so again, subnets do not give you L1 security. They leverage L1 security by having checkpoints to the parent, which prevent malicious attack rolling back to distant past in the future. And also this firewall property. So if there is a security violation on an L2 or L3 or below, so this affects just this branch, and it doesn't affect other L2s that are basically siblings, for example, from the corrupted L2. And we focused on decentralization. So at no point will you see centralized sequencer, centralized proposer, and so on. So this was our trade-off, I would say, in prioritization of technical challenges that we tackle. So unlike some other projects, we focused on decentralization first and building the system that actually doesn't have a single point of failure. So this goes both for like censorship resistance and data availability. So this gives a short overview, like what of the main features of IPC, and then of course the question, like how does it compare to whatever you can imagine? So sidechains, rollups, validiums, plasma, some terms that you never heard of, like there were tons of on Raul's slide, right? So how does it compare to all of this? And in the rest of this talk, I would like to go through major ecosystems and just briefly compare IPC to those. So let's start with positioning with sidechains. I said like IPC is essentially a network, recursive network of proof of stake sidechains. So what are sidechains? These are just chains that connect. So this is the definition taken from the original paper in 2014. That there is a two-way peg that allows funds to be transferred from parent chain to sidechain and back. So IPC is more than that, right? But it provides you these bridges and this capability. So in a sense, you can classify it as a sidechain protocol. It's a bit more than that, as we will see. And what else you get is this native L2 proof of stake in L1 tokens, hierarchy and recursion, native crossnet communication, and this is our design principle that I didn't stress so far, but our solution is relies on FVM and IPLD. So you have content addressing, and you have ability to program WASM smart contracts basically built in. And this is not what you have typically in sidechains, right? So compared to, for example, to Bitcoin L2, so in Bitcoin L2, the dominant technology is Lightning Network, of course, right? Which tries to take Bitcoin from just being the anchor of money to a global payment system. And the challenge there is, of course, scalability decentralization, because if you could do it, of course, you would scale L1 to support transactions for all people in the world. But that's not going to be decentralized, right? Because Bitcoin stores all transactions on every full node. So imagine that you store all transactions for 8 billion people on the planet, and you need to store them in every full node. So basically, this bloats the full node, and then you need to go to centralized solutions. So this is like the origin of block size wars, if you followed in Bitcoin community. The choice that you don't increase block size, but go to scaling to L2s is basically what's enabling decentralization. And of course, you have a bit less security as you go down the stack. But of course, I mean, this is just mainly for payments, and it's not even enough, right? Because there are challenges. If you want to support 8 billion people, you need one transaction to open a channel and one transaction to close the channel, and you can do quick calculation. You will see that this won't scale on current Bitcoin for the entire world. And this is why there was a drive to move to sidechains. So if you see now Bitcoin layer 2s, current ones, they will be sidechains, but unlike IPC hierarchy, these would be isolated from each other. So the user would need to, for example, to go from a liquid to RGB, you need to do a transaction to mainnet, and then manage it yourself and go to another chain, and this is the difference that we have in IPC. So this communication among IPC subnets is seamless. Okay. This is a brief overview of like the main Bitcoin sidechain-based L2s. Some of them have smart contracts, some of them not, right? So, and recently, with the move to basically support arbitrary computation of Bitcoin, there is like also the move to have more elaborate L2s on Bitcoin as well. So, namely rollups. And rollups come from Ethereum ecosystem, to which we switch next. And Ethereum ecosystem is arguably richer than that of Bitcoin in terms of L2s, right? So there is this moving terminology, right? So which term do you use to characterize certain scaling solution? But I took this post in which essentially the naming convention comes from the fact like where do the input transaction for a scaling, for an L2 live? So namely, if a scaling solution puts its transactions to L1, which is important for data availability and basically fraud proofs, etc., so that you can repeat the transaction if the L2 misbehaves and so on. So it has certain security properties. So if you put this input data to L1, then you're talking about data on chain, and you're talking about rollups. So rollups, in short, they put transaction data pertaining to L2 on L1. Okay? And if data is off-chain, then like similarly to IPC, as I said, in IPC we have data availability scattering, replicating the data across validators of a subnet. Then we are talking about Validium and Plasma depending on how you prove the state on the parent net. So Validiums is if you use snarks and starks, so zero-knowledge proofs. And if you use fraud proofs, like in optimistic rollups, you will be talking about Plasma. And in this talk, unlike in Bitcoin, Ethereum community tends to call not all solutions, so solutions that don't give you Ethereum security, in some sense, not L2s. But in our talk, like L2s are all scaling solutions, even if they have lesser security. Okay, so let's position IPC with respect to Plasma. So what is Plasma? I took this definition from the Plasma Group website. So essentially, Plasma chains are sort of like sidechains, except they trade off some utility for extra security. So like sidechains, Plasma chains have a consensus mechanism that creates blocks. However, unlike sidechains, the root of each Plasma chain is published to Ethereum, so L1. And you see the similarity here. So like Plasma, which leverages Ethereum for like posting certain key information to its rootnet, this is the approach that we adopt in IPC as well. So IPC can be, it's probably closest in this picture to Plasma, but what you get additionally is similarly to sidechains, this hierarchy. So basically the fact that you can go recursively deep to L3s and so on, and this is important for gaming and other use cases as we discussed and as we will discuss today. You get native cross-net communication, and you get this fact that it's based on FVM and IPLD. So just a short takeout from this presentation, in its current state, compared to Ethereum ecosystem, IPC is closest to Plasma. Okay. But, I mean, Plasma was popular in Ethereum ecosystem in 2018, right? So now it's more about roll-ups, and we often get the questions like, but why don't you take the roll-up way of doing things like posting data on chain and so on? So we'll tackle this now. Because but as you see, majority of the solutions, this is taken from L2Bit, majority of the Ethereum scaling solutions based on rollups are in this stage 0 and stage 1. So roughly speaking, you can check what this means exactly, but this means that they're not decentralized. So essentially that they have dependency on the centralized sequencer for many things. And this is what we try to avoid with our approach to our design from earlier. As of 2 days ago, Plasma is back officially. So this is like, you have a blog post from Vitalik and his talk at L2 Days, where basically he proposes, and this was a bit of a shock to Ethereum community at L2 Days, but like he proposes going back to Plasma combined with UTXO data model, and I have to say, so more looking like Validium, so ZK proofs to actually prove the computation on the parent net. So it's interesting because we kind of went there. We don't have, as you will see, we don't have ZK proofs for proving things. Our proofs are, as they will be implemented actually in the following weeks, they will be based on more looking like optimistic rollups, so fraud proofs based on equivocation proofs and so on. But we are going in this direction, right? So we were going in this direction from the start. Okay, so what about Validiums? Validiums like similar to Plasma, but they have ZK proofs when they post this key metadata to the parent net. So we are not there yet, but this is on our roadmap, right? So, and we have several approaches that we are exploring, and the probably like we could do it in-house, but there are so many efforts out there, and like in PL network, you have teams like Lurk and others who are developing this technology, and in broader ecosystems, you have like maybe folks that are working on centralized roll-up sequencers, and basically we can explore compatibility between two approaches. But if you will, IPC will go in Validium direction, basically in Ethereum speak. What it will not do, it will not go in the roll-up direction, and I will explain why. So roll-up direction, like we could, but I will explain why this is not necessarily a great idea. So recall that roll-ups put their input transactions on the main chain. So if you will, if you do the recursion, if you like do it naively, then this would pop up. So L3 would put input transactions to L2 that could put input transactions to L1, and this is not going to scale at millions, billions, and trillions of transactions per second. Like it's just not, because it's going to blow L1, and then we have the problem from Bitcoin again. So basically full node requirements grow, and basically you centralize the main network. So there is this decentralization, so that's your decentralization scalability trade-off that just pops up. And you have issues with data availability and whatnot. So this is the main reason, right? We are more oriented to data off-chain and data availability on a subnet with potential archiving on Filecoin in future and so on. And again, I'm referring to L2 Days. It was a great event in the past 2 days. So there, the bulk of Ethereum scalability solutions are talking about mainly about two things. So data availability, how to implement it well, for rollups, and decentralizing rollups. So if you will, we focused on addressing these two problems first by the design, by decentralizing the subnet in the first place, and doing the data availability across subnet validators and full nodes. So which brings another interesting use case to IPC, which some of the PL network teams are exploring, is how to use actually IPC to decentralize a rollup on Ethereum ecosystem. And there is a project, if you heard Sashimi, that's actually trying to go in this direction, and it's an interesting thing, right? Because you will need a data availability solution, you will need to decentralize, is it a proposer, is it a sequencer, and then there is a nice effort to use IPC. So that this team is not focusing on it directly, but there are people who are. Okay, and for the last comparisons, I have in other ecosystems. So we are going from Bitcoin and Ethereum here to Polygon, and there are others. So I will not do an exhaustive comparison here. But the bulk of the ideas that we are using are not necessarily unique. And Polygon Supernets is the scaling framework for Polygon, that launched earlier this year. And I try to basically have the comparison here. So let's focus on the lower table first. So this is like what consensus is used within a particular subnet. And there I would say this is the same class of protocols. So we developed initially for IPC, for Lotus-based, Lotus is a Filecoin client. So for Lotus-based IPC, we developed very scalable consensus protocol called Trantor. And then when we shifted the stack to Tendermint, then we inherited Tendermint. But basically, at the moment, Tendermint or Comet BFT is not really flexible, so we are changing this in future and making it more flexible. But in principle, if you compare Polygon supernets to what we have currently, they are the same class of leader-based protocols. So Polygon has IBFT, it's leader-based, and we are working currently on Tendermint, which is also leader-based, so it's basically comparable. Both are proof-of-stake subnets, so basically when you spawn a subnet, this works in a very similar way. So that's interesting. What's different, and I highlighted it here, right, is this recursion. So if you will, like, if you focus on the lower right corner, there is like a Polygon link to Ethereum, right? So there is a bridge to Ethereum. And then you can spawn supernets essentially as L2s off of Polygon L1, but then you stop there. And again, this is a subtle but important difference which enables many use cases. So as you hear in the afternoon, like for gaming, for ephemeral subnets, it might seem a very like, okay, I mean, they can still spawn from L2s to L3s and so on. Yes, but like in sidechain to sidechain non-automatic communication, like you need to do these things manually, right? And then you need to manage them manually. And we have it in the design from the onset. And basically, this is the main difference. We have difference in the data model. Of course, we have IPLD and so on. But other things, so if you want the closest technology to ours, I would say this is Polygon supernets at the moment with this very important difference. Okay? And another close one from one of the major projects is Avalanche subnet. So Avalanche actually uses the same term, subnet, as IPC. So there the difference is a bit more elaborate. Of course, there is no recursion in Avalanche design, but also checkpoints, like you don't have this leveraging of parent net security as we have it in IPC. So the differences are subtle but important, right? So this fact that you can go down, so if you want to summarize, right? So if you want to know what IPC unique value proposition is, I would characterize it like this. So you have this hierarchy among subnets and recursion, and you have the orientation towards FVM and IPLD. And this is what you get from us. And it's subtle but important. So it enables use cases, it enables unbounded scalability, and you don't need to rethink your system for like Web 2 workloads later down the road. We have a lot of stuff to work on, like to improve our fraud proofs, to incorporate ZK proofs to our designs and so on. But like we focused on many complementary things that other projects are not focusing on because we were failing decentralization and scalability and making the right trade-offs between them and prioritizing those. And for free, you get this design that you can deploy IPC today to EVM-compatible chains, like Filecoin and Ethereum, but nothing in principle prevents, like theoretically, nothing prevents in future even extending to chains that have less expressivity than EVM. And that's it. Yeah. Thanks a lot.